This section is about going from one particle to many particles when using the partition function. In other words, how do you know when to use the factor of 1 over n factorial? So we need to have a solid definition of what distinguishable means. When we look at the case of the ideal gas, we know that this is an indistinguishable system, and when we talk about the system of identical harmonic oscillators, we know that this is distinguishable. This is what we see in books and in class. A lot of us take it for granted, and we don't really know what actually makes a system distinguishable. Many people will say exactly the same things that they just read in books, that the oscillators are distinguishable because they are representations of energy levels available to the system. They are not particles or even quasi-particles. They are phonons or photons which distribute themselves over various oscillator levels. I think there is a better way of explaining this. So let's see. Consider three systems. The first one, I'm gonna call it system A. This is a collection of objects or particles, each having a Hamiltonian of this form. The second one, call it system B, is a collection of particles having a Hamiltonian like this one. And of course, system C with this kind of Hamiltonian. In each case, the objects making up the system have a Hamiltonian HI, so that the total Hamiltonian of the system is the sum of the Hamiltonians. Take a look at the Hamiltonians one more time. For those who need to know what they are, here it is. This one is an object free to rotate about this axis. Let's say this is one of the principal axes of the object, with corresponding moment of inertia. As I said before, all objects in the system are identical. Or it could be also a particle constrained to move in a circle, free to rotate, but in this case, the moment of inertia will just be mr squared. It doesn't matter. The next one is just a particle free to move, no interactions between the particles. I think you can see that easily. And the next one, I just have no idea. I just made it up. And the question is, which of these systems are distinguishable and which ones are not? Pause the video and write your answer on a piece of paper. Okay, so if you said A and C are distinguishable, then you don't need to watch this video. Go to the next one. If you didn't, then here it is. A and C are distinguishable, and B is not. And here is the reason why. If you live in a city where all the cars, which are free to move, are identical, same company made them, same model, same year, same color, and no plates, then you will never be able to tell the difference between them. They will be indistinguishable. But if you live in a city where all the houses are identical, they still be distinguishable, because you can always tell the difference between one and another because of the streets in which they are located. In other words, they are fixed in space and they have fixed coordinates. They have an address. In a system of particles with this Hamiltonian, the particles are free to move. They are all identical and with random motion. If you carefully follow one particle, you can claim that you can tell the difference, at least for this one. But the truth is that you lose information about the other ones. And by the way, the only reason you can tell the difference is because this one I painted in color red. But can you tell me, let's say, about this one? Or that one? What about this one right here? And that one? Just like the cars in the city, you cannot tell the difference. This system is indistinguishable. With systems like this one, we use this kind of partition function. Now imagine a system like a collection of harmonic oscillators. They are all identical, they do move, but they oscillate about a point of equilibrium, and this point is fixed in space. It has coordinates that denote change. They have an address, and because of this, you can tell the difference between one and another. So this system is distinguishable. For this kind of systems, you use this partition function. Now let's go back and see the Hamiltonians. So this one we already know is indistinguishable. Now take a look at this one. These are free to rotate, but the point of rotation is not free to move, so it's fixed in space. This point, in other words, has an address, just like the houses. So this is distinguishable. Now for this one, I have no idea. But it doesn't matter, because I can see that the only variable is theta, and there is no term for the translation. So whatever they are fixed in space. They have an address, so they are distinguishable. I'll give you another example. Take a look at this Hamiltonian. This one is for magnetic dipoles having magnetic moment mu in an external magnetic field B. They are free to move on the theta direction, but there is no term for translation, so they are fixed in space. Therefore, they are distinguishable. So now you know. I hope it was useful. So remember, if somebody needs your help, don't just quote the books. Explain it in the most simple way. Thank you for watching and good luck.